Great, so the next thing that we're going to do this morning is we're going to talk about some of the other problems. So this is focusing on problems that are a bit like problem 12 on your worksheet, and problem 13 is very similar as well. So in problem 12 we have the concentration of an acid, and we're given a pH and we want to know what is the Ka. So the key to understanding how to do these problems is to think about the acid dissociation that's happening. So here we do not specify what the acid is, and that's okay. We can actually just write a generic equation, and I usually use HA, so the H is the cation part and the A is A for anion. So we talked about how that's going to be our basic structure for a Bronsted-Lowry acid. So it's interacting with water and it does its acid dissociation equation, and that's okay even though it's a generic equation. So the key here is noticing that if we have a strong acid, so if HA is a strong acid, then the pH will just be based on the concentration of the solution. And we can check that. We can just quickly say, okay, well, if the pH is minus log of 0.125, then our pH, oops, what happened there? Let's try that again. Minus log of 0.125. Okay, so what's going on? I don't know why it's doing that. That's very weird. Okay, well, anyway. So 0.903 is the pH of a strong acid with concentration 0.125 molar. This pH is a larger number, and we remember that if we have a larger pH, it means that we have a weaker acid or a less concentrated acid. So higher pH equals less acidic. And since we know for sure that this is the concentration of our acid, so we can actually put that for our initial concentration of whatever this is, we can tell that this is probably some kind of a weak acid. But the other thing that we know is that the pH tells us pH is minus log of the concentration of H3O+. So we're going to use this pH to figure out what the concentration of the H3O+ is in the solution. And that, if we think about our ice table, is going to be the equilibrium concentration of the H3O+ right here, because the pH of the solution is happening when we are at equilibrium. So we're actually going to use the pH to work our way backwards through this problem with our ice table. Okay, so let's go ahead and set that up. We've got the pH, so we're going to solve for the H3O+, and as you remember, that's going to be 10 to the minus pH, just from our last video here. So let's go ahead and do that calculation. 10 to the minus 1.254. Remembering that we have 3 sig figs here, so our H3O+ is equal to 0.0557 molar. All right. So this number tells us how much this acid has dissociated. This is equal to the X that we normally put in here. And we also have to remember that initially we would have had 0 H3O+ and also 0 of our anion. And so if this acid dissociates 1:1 to make H3O+, it's also 1:1 to make this anion. And so that means that this number is also 0.0557, because both of these went in our ice table the same amount. Okay? So now we just have one more number. We know that this would have changed by the same amount that this increased by, and now we just have some math. So 0.125 molar minus X, which is 0.0557, is going to be the equilibrium concentration of that acid. 0.125 minus 0.0557 is equal to 0.069 molar. And now we're ready to set up our equilibrium constant expression. So we're trying to find the Ka this time, and so this actually goes back to some of the calculations we did in the last chapter, where we set up our equilibrium constant expression, and then we were given the equilibrium composition of the system, and we used that to calculate what the K value was for whatever our equilibrium is. And that's exactly what we're doing right here. So this normally, these would be unknowns in some of the problems that we've been doing, but this time we actually just know what they are. So we have calculated them, and we've got two of the same. I'll just square that, divided by 0.069. And remember that our equilibrium constants are unitless, so we don't have to worry about putting the units in. 0.0557 squared, divided by 0.069 equals 0.04, and I'll round up. Oh wait, I won't. I've only got 2 sig figs there. So I'm going to have a Ka with only 2 sig figs, so 0.045 is the answer for this question. And we are going to just go ahead and stop there because we've solved the problem and answered our question.